And we're good to go there. All right, welcome. My name is Ryan Holger with Temperature Equipment Corporation. I will be your tour guide for the next hour. We'll be talking about the Illinois Energy Conservation Code, specifically how it relates to rooftop units and some of the challenging things with getting your rooftop installation to comply. As I mentioned, this webinar will be recorded, and you'll be able to refer back to this at a future date if you wish, or send it to a coworker. Additionally, if you are on the webinar and need PDHs, professional development hours for professional engineers, PEs, if you signed up as such when you registered, you will be getting certificates in email next week. In order to get a certificate, you must participate in the webinar, and you must answer correctly the poll questions as they come up throughout the webinar, very much just like all the other ones we've done in the past. So with that, we'll get started. When my mouse cooperates, if it ever cooperates. There we go. All right. So, as you're probably aware, the Illinois Energy Code is the the International Energy Conservation Code 2015 version. Illinois is one of numerous states that are on this code. We've been following the IECC since 2006, and we update it every 3 years, and the current version is 2015. We will move to the 2018 version very likely on January 1st, 2019. So we got about 2 more years on this code. We've been on it for a year, and we got 2 more years on this exact version we're talking about. This code does apply to both new construction and existing work, and it does apply to both residential and commercial. But obviously today we're sticking on the commercial path with packaged rooftop units. You might want to write this website down on the bottom of the screen here. That is the state website that lists information about this code and tells you, that it is in fact the code. And then specifically, there's also, I don't know if I got my little highlighter thing here. There's a little spot over here for Illinois amendments, and if you're on this website, you can click on that, and you'll download, I think it's like 12 or 15 pages of amendment language. Now, most of it does relate to residential stuff as far as HVAC is concerned, but you may want to have that in your file just in case. All right, the other website of interest is the City of Chicago website. In the past, the City of Chicago has historically had its own energy conservation code, and they've had one before the state did. But as you probably know, the state code applies everywhere, including the City of Chicago. So the city's website specifically states that you have to follow the city code and the state code. You have to follow both, and hence whatever thing is more strict is the one you'll have to do for your particular discussion, because sometimes they're not always historically in sync. And that's been on the state website or city website for about 15 months now. More recently, in September, the city issued this information, which basically says that they've updated the city code to be more in sync with the state code. So essentially, they're the same thing now. So if you just follow the IECC 2015, you should be good everywhere in Illinois. One other thing I want to point out with the City of Chicago Code while we're talking about it, that's not directly related to the Energy Code, but it is very related to packaged rooftop units. Historically, the city has required you to add 15 feet of external ductwork to packaged rooftop units for the outside air intake to get that intake away from the power exhaust on the unit or the heat exhaust and all those kinds of things. That is no longer a requirement of the code. For the past 13 months, you do not have to do that in the City of Chicago anymore if it is a packaged rooftop and it is properly rated. So you do not have to have that 15-foot extension on there anymore. Now, if there's some other exhaust source from the building, like toilet exhaust or some other combustion exhaust that's unrelated to the rooftop that's near your rooftop intake, you would still have to do it in that case. But the rooftop itself, you don't have to be 15 feet away from itself anymore. So that may help some of you guys with some of your labor and effort on the roofs there. All right, you've probably seen this slide before. Lots of us use the exact same slide because it shows the history of energy codes, and actually I need to get it updated or steal it from whoever I stole it from the first time and get their update to show the 2015 on here. But over time, the codes get more and more stringent, and for the past 15 years or so, we've been updating the codes on a 3-year cycle. Both ASHRAE 90.1 and the International Energy Conservation Code both update every 3 years. IECC updates 18 months after ASHRAE, approximately, because a lot of the information in IECC comes from ASHRAE 90.1. So we're on 90.1. 2013 version would apply to the IECC 2015. This new code that we have, I say new, it's been out for 15 months in Illinois, but this new code that we have is about 9% more efficient than the old code. And the vast majority of that efficiency is coming from rooftop units, in my opinion, as far as HVAC is concerned. That's the biggest change. You may have seen this state map before, or one like it. Illinois, Maryland, and Alabama were the first states to go live. Maryland went live like immediately, and then Illinois and Alabama went live together last January 2015. But since then, 9 other states have come on board, and we have a total of 12 states that are following this code, with several more considering it. Wisconsin being the closest one that's probably going to go live pretty soon, and Michigan is another Midwest one. They're live on the residential, I believe, already, and coming soon on the commercial, I think it is. So if you're from one of those states and you're watching, everything we talk about today is going to be for Illinois, but it's going to be like 99% of whatever you're following there, because you're probably not going to have a bunch of crazy amendments. Probably. So when does the code apply? The old 2012 language and the 2015 language are a little bit different, but I think essentially they're saying the same thing in a different way. So you have to follow the code for everything. So new construction is obvious, but it's not a new construction only thing. You have to do it for additions. You have to comply with it for alterations, repairs, renovations. Pretty much anything that involves you doing work at the building to pull a permit is going to involve you complying with the code. Now, with that being said, you don't have to make the entire building or even the entire HVAC system comply with the code if you're changing something. Only the thing you're changing has to comply. So, for example, when we change out a rooftop unit, the rooftop and its related components have to comply, but it doesn't mean we have to go change out the boiler or something else like that, right? So we take off the rooftop efficiency and its associated attached accessories like economizers and things like that are going to have to be updated with that. So basically whatever you touch has to comply. There are 3 ways to comply with this code. We're only going to talk about one of those today. But the first way to comply is to follow ASHRAE 90.1. ASHRAE 90.1 is the energy standard for the entire country. It's the basis of this code anyway. But if you don't want to use this code book, you could just follow ASHRAE 90.1 and you would automatically comply. ASHRAE 90.1 has several compliance paths of its own that we're not going to talk about today, but you could certainly do that. The one caveat with that is if you go the 90.1 route, the entire project has to go ASHRAE 90.1. You can't cherry pick and say, oh, I'm going to do the rooftops from IECC, but I'm going to do the windows from 90.1 or something like that. The whole project goes one way or the other way, right? So that's number 1 on here. Number 3 is like an energy modeling option within IECC. So you'd have to do the mandatory portions of the code, which are the ones that are listed there on number 3 on the bottom. And then you'd have to do like an energy model of the building. And then you have to beat that energy model with your building by 85%, or beat it by 15% to get 85% of the energy. So you can do it that way, or you can do number 2, which is what we're going to focus on today, which is the prescriptive compliance path. It basically says you do everything that's mandatory in the code, plus you do everything that's prescriptive, thou shalt do A, B, C, D kind of thing, and then you automatically comply. So that's the route we're going to stick on today, the basics of the code. You don't have to do prescriptive things if you take option 1 or 3. But for most people on a simple rooftop job where you're changing out a couple rooftops, you're going to be going down number 2, the prescriptive path. All right, so we have quiz question number 1. This is especially important as a reminder for those of you that need PDHs for professional engineers. You do need to answer these questions correctly. So I'll launch the first question here. Read the whole question before you answer, please. So basically, what is the current Illinois Energy Conservation Code? Your choices are ASHRAE 90.1 2010, 90.1 2016, IECC 2015, 16, or 12. So I'll give you a minute to answer that. If you guys would be so kind, if you have any questions as we're looking at stuff here, please type them in the question chat box down in the bottom right-hand side, and I will try to answer them. As you guys are doing your poll questions, I'll try to glance over and look at some of the questions that you guys have for me, and I'll try to answer those. All right, 75% of you guys have answered, so I'll give you another couple seconds here, and we'll close it in 5, 4, 3, 2, 1. And we'll pop the answers up here for you. And as you know, answer was C. 91% of you got it correct. IECC 2015 is our current Illinois code. All right, right now nobody's got any questions for me, but we just started out, so that is pretty normal. All right, so let's talk about stuff that's specific to rooftops that are in this code. The first thing is you're not going to find a section of the code called rooftop units. In fact, you probably won't even find the word rooftop units. As far as the code is concerned, rooftops are basically DX packaged HVAC units, but you won't find a section for that either. You have to go read all of the individual sections and decide which of them apply to a rooftop. Because unlike a boiler or a chiller or something like that, a rooftop is doing lots of things. It's doing your ventilation air, so it's got outside air intakes, it's doing your cooling, it's doing your heating, so it's got lots of components in all in one box. So the pieces of what you have to do are scattered all over the code. So first thing is calculations for loads and equipment sizing. Just like with all systems on a rooftop project, you need to do a load calculation. That is required by code. It's been required for a while. Some areas enforce it more aggressively than others. This is a statewide code, but in Illinois, codes are enforced at the municipal level. So some cities are more aggressive than others in terms of policing the code. By the way, I should mention that even if your town doesn't police the code, or even if your town doesn't even have an inspector for that matter, you still have to comply with the state code. It's not an optional thing. It's not a municipality telling you have to do it. It's a statewide code, so it's essentially the law everywhere. So even if you're not getting flagged by an inspector, you still got to do this stuff. So you do need to do a load calculation in compliance with ASHRAE Standard 183 or something very similar to that you can get approved. But your normal load calculation programs like Trace and HAP and DOE and these things will be able to comply without any difficulty. So you need to do a load calculation, and then you size your actual equipment to match that load. The way that this is written, you're actually not allowed to oversize the equipment at all. So the heating and cooling equipment shall not be greater than the loads calculated. Now, it does say that obviously with a package unit, you're not going to have identical heating and cooling loads that match up with every manufacturer's scenario. So you are allowed to round up to the nearest heating or cooling size to try to match with the other one, right? So if you need 7.5 tons of heating with whatever, I don't even know, 200,000 BTUs of heating, but you have to get one that has 220,000 BTUs of heating, you can do that to get the cooling to work out right and vice versa. So you are allowed a little bit of flexibility there, but you can't just start upsizing things and going up to the next whole random size kind of thing. One part of the load calc, obviously, is what outdoor air temperatures do you design for. I should have made this a poll question just out of curiosity, but I still hear a lot of people saying they design for 95 for cooling and -10 for heating in Chicago area. And those numbers, I don't know if those were ever right, but they certainly were not right in the 20 years that I've been in the industry. Those have always been really, really, really exaggerated numbers. If I look at the ASHRAE handbook, which you could argue is the de facto standard for what these things should be, if I take the most stringent cooling outdoor air temperature and I get, to get to me the biggest equipment possible for O'Hare Airport, which you would say is Chicago's central airport, 91.4 degrees is my cooling design temp. And I could take the less aggressive numbers, the 1% or 2% bucket, and have even a lower temperature. But most guys will design for the 0.4 number. So 91.4 degrees for cooling and -1.5 for heating are my outdoor design temps in most of Chicagoland. And then if you're in some of the suburbs, like I live in Aurora, -5 is my heating design temp. But most of these are pretty similar to each other. And you're not going to find any that are 95 in Chicago area, and you're not going to find any that are -10 on the heating. So getting these outdoor temperatures right is one main component of getting these units sized correctly. Most packaged rooftop units are, in fact, oversized, as you probably know. If we look at those outdoor temperatures a little different way, instead of looking at the most extreme design temps, if we look at a profile of all the outdoor temperatures and how many hours we spend at those temperatures, and this example is for Chicago, but we can do other cities as well, obviously. The EER of a packaged rooftop unit, or most mechanical equipment for that matter, energy efficiency ratio, that is tested at 95 degrees ambient. And that tells you how efficient your unit is at that outdoor air temperature, right? But you can see in Chicago area, we don't hit 95 degrees at all on an average basis. Yeah, we'll have some random day every few years where it's 100 degrees, but on an average, like rolling 30-year cycle, we have almost no run hours above 91, 92 degrees. So a 95-degree test point is not super interesting to us, or most of the country for that matter. There is a newer metric called IEER, Integrated Energy Efficiency Ratio. This is the part load efficiency of mechanical systems such as rooftop units and split systems. And this tests the efficiency when it's not a peak scenario. So this is more appropriate for what we care about here, where we're trying to figure out, well, how many hours are we running at 65, 70, 80, 85 degrees. That's more interesting to me than a 95-degree test point. The way IEER works is they actually test it at 4 different points, or they rate it at 4 different points. One of those points, point number A, is the traditional 95-degree max capacity, EER type number. Then they do the same kind of test, part loaded at 75%, 50, and 25%. Then they heavily weight the 50 and 75% numbers. The 100% and 25% numbers get very little weighting because the 100% number hardly ever happens, and a 25% number I should have some assistance from the Economizer at that point. So really all the weight goes towards the middle. And those efficiency ratings are what's used by the manufacturers and AHRI to rate the equipment, and they also fit into the code table, which is illustrated right here. So first thing to know is that if you have small equipment, small meaning under 65,000 BTUs, so less than 5 tons of cooling, you do not use EER or IER. You use SEER, Seasonal Energy Efficiency Ratio, which is the residential testing metric. Even though you're doing this in a commercial building, in our case, you're still going to use that metric because that's how that equipment is tested. So for small systems, 5 tons and under, you need to have 14 SEER as your rating point. When I get to bigger systems, 65,000 BTUs and up, I'll have a couple rows to look at. One is electric resistance or no heating. Then the other row is all other heating, which would mean gas heating in our case, or I guess it could be hydronic heating. But for most of us, it's going to be gas heating. And for today, it's going to be gas heating. So if I got a quote-unquote 10-ton unit, that's 12,000 BTUs of cooling, I need to have 11 EER and 12.6 IEER. I have to do both. It's not one or the other. I have to meet both metrics. And then as the units go up, as you can see I have highlighted in yellow there, as the sizes go up, I will become more and more little lenient on what the requirements are because the manufacturing volume is not as high. But I'll still have to do both. I'll have to have the full load and the part load efficiency. And generally the smaller units need to be more efficient than the bigger units. This is a software tool that we're going to use a couple times today, actually a lot of times today, to illustrate the effects of what some of these things have on code. It's a free software tool. It's actually the subject of next Monday's webinar. If you're interested, we do these webinars pretty much every Monday at lunch. So next Monday is how to use this software if you're interested in that. But it's called Commercial Invest. It is a carrier software tool, but it's generic. It has multiple manufacturers in there. It just uses the published ratings of those manufacturers. But for what you can do is you can run different examples of either 2 brand new units and see which one is better in terms of efficiency, or an old unit versus a new unit, which is very commonly what this is used for. But I tell it what my cooling load is on the bottom left-hand side over here. In my case, I told it I want to use the IEA energy data. I could have punched my own utility data in, but taking the state average from the Energy Information Agency is just easier, so I did it that way. And then I have one column here for my base unit, one column for my better unit, if you will. In this case, they're both brand new units with they're both, either one I'm choosing between a brand new one. This is an entry-level unit, which is the least efficient thing I could have found to buy brand new, right? However, the one on the right-hand side is an IECC 2015 compliant unit. So exact same units, same sizes, same tonnage, same motors, same accessories. I just changed the model to the higher efficiency one, right? So we can see what it's going to actually save. And in Chicago, it is going to save me $27 for a 10-ton unit. 1% energy savings. It's not super exciting. I know you were expecting something better, like 2%. But the efficiency of the rooftop from a refrigeration standpoint, which we're talking about here, we're kind of at the upper bounds of that as it is. But it does make it a little bit more efficient, and in some climates it may be a bigger deal than other climates, but here it's pretty minor. Some of the other things we talk about today will have a much, much bigger effect on energy savings than just going to a IEC 2015 compliant unit. I mean, you still got to do it. You still got to buy this unit and install it, but just don't expect some massive energy savings versus an entry-level unit. Now, you have a lot of energy savings versus the 15-year-old unit you're ripping off the roof, right? But you won't have too much otherwise. So let's do quiz question number 2, and then while you're doing that, I'll read your guys' questions you have for me. All right, so question number 2, which of the following does not, N-O-T, which of the following does not have to comply with the IECC? Choices are new construction, alterations, additions, historic buildings, and repairs. I didn't specifically mention in my discussion which one did not have to, but 4 of these I said did have to comply. So that should make it fairly easy for you to figure out which one does not have to comply. Hopefully I didn't word the question too confusing here. All right, while you're doing that, I'm going to read some of your questions. Tom asks, if we are modifying sheet metal distribution on an existing RTU, does the unit need to be updated? The answer to that is no, Tom. The rooftop unit could continue being the same one that's always been on the roof, and then the sheet metal would have to be updated. So whatever new sheet metal you put in, right, that would have to comply with code. So let's say you did a new branch run off to some new office that never used to be in the building before, right? That 30 feet of duct you ran to that new office, that entire 30 feet has to be designed and installed to code, and we'll talk about what's required for ductwork a little later today. But the existing ductwork that you didn't touch and the rooftop that you didn't touch can just be left the way they are. Let's see, we got one from Steve, which is not really a question, looks like more of a clarification. He says, technically part 600 of the State Energy Code, section 600.200, standards for state-funded facilities. The code for this is ASHRAE 90.3, not IECC, so technically there are buildings where ICC does not apply. I'm going to have to talk to you on the side on that, Steve, and I got a feeling most of Steve's questions I'll probably have to talk to him on the side because Steve always has very intricate questions. So Steve, we'll talk about that later if you don't mind. I'm not quite sure where we're going with that. All right, so everybody has answered the poll question. I will close that now. And I guess I did word it a little bit more confusing than it needed to be because only 46% of you got it correct, which is historic buildings do not have to comply with the code. I did specifically say new constructions, alterations, additions, replacements, and repairs all had to apply. I did not mention historic buildings. I should have pointed it out a little better probably. Although more interestingly, 1% of you said new construction didn't have to comply, which tells me that you're just messing with me at this point, because obviously that would have to. All right, we'll move on. All right, so economizer. We're going to spend some time talking about this because this is a pretty active part of what a rooftop is, and there is some good energy savings from it. Most of you guys know what an economizer is. It's essentially our way of opening a window in a commercial building where windows either can't be opened or they're not easily opened or they're opened by occupants that don't know what's going on, right? So instead, we open a window inside the mechanical unit and bring in the cool, free air that way. So on mild days, I want to use the outdoor air to free cool. There are 3 main ways we have done that historically for our climate zone. Dry bulb temperature, which means I don't care how humid it is. If it's below a certain number, use the economizer for cooling. 60 was a pretty common number we used to use back in the day. If it's below 60, open the economizer for free cooling. If it's above 60, run your compressors. You could also do enthalpy, which is essentially, from a layman's standpoint, looking at temperature and humidity. And if both of them are good, then I'll go ahead and use my economizer instead of compression. And then one step better than that is differential enthalpy. So I don't care how warm it is outside or what specific number, right? I just care, is the outdoor air cooler and drier than the return air? Because my air can only come from one of 2 paths. It comes from the outside or it comes back from the space. So whichever one is cooler and drier, hence lower enthalpy, I'm going to use that one, right? So that's the basic economizer discussion. When are economizers required? For most systems in Illinois, we would climate zone 5A for Illinois, 54,000 BTUs and up, I'm going to have an economizer, right? That's 4.5 tons essentially. This is actually less stringent than the 2012 code, where we had to do it for 33,000 BTUs and up. So this has been relaxed a little bit. It's one of the few things in the code that got less stringent than the previous version, probably because, as you might know, this section does not apply just to rooftop units. It applies to all systems, right? So all fan cooling units, right? So if I have a fan and I have a cooling coil, I have to do this. So that means if I put a residential split system, a furnace and an AC in a commercial building, I have to do this. So 3 tons was making it pretty tough to do some of these things on a residential system in a commercial building. So by doing this new cutoff point, it makes it more cost effective overall. There are some exceptions to it where you don't have to do the economizer. The big ones that would come up in relation to rooftop units are if this was number 4, a residential space, then it's 54,000 times 5 becomes the limit. So essentially you don't have to put you don't have to put economizers in commercial buildings if the space it's serving is residential. Number 5 comes up a lot for like a church or something. If my system's only going to operate on Sunday morning for 2 hours, then I wouldn't necessarily have to put an economizer in if I wasn't using the space for anything else really. Supermarkets, and there's a few things like that where there's some exceptions. If I have heat recovery systems, if I have chilled beams, those kind of things might not have to do it. But for a rooftop job, I'm probably going to have to do it. As soon as I get basically 5 tons and up, I'm going to have to do it. It's kind of a good check figure in your head. There's the climate zones. So we are climate zone 5A, right? Green is 5, A is to the right of that middle line there. So we're the moist climate zone. So these exceptions over here, number 1 and number 2, don't really apply to us, right? So we're going to have to put economizers on our rooftop units. Once you put the economizer on the rooftop unit, these are the set points that the code is going to require me to utilize. Since we are climate zone 5A, that means my outdoor changeover point is going to be 70 degrees instead of 60 degrees. So previously, if I was going to, or whatever I was using, some of you guys probably still use the old 55 number because someone told you to use that 25 years ago, the first day you went on a job. So now if it's 69 degrees outside, I'm an economizer day, and I got to open up my economizer for free cooling. Now I know you're thinking, I can't really cool your building at 69 degrees, right? So that's true. I'm going to have to run compression with the economizer in most of those cases, which we'll talk about in a little bit. But you no longer set the economizer for 55 or 60. You now set it for 70 degree outdoor air temperature. If you're doing enthalpy, you'll set it for 28 BTUs per pound of dry air. And you can also have, in addition to that, a 75 degree maximum cutoff temperature as well. Some of the controllers, like the very popular Jade controller that is used on most manufacturers' rooftops nowadays, does not have an exact setting for 28. I think it's like 26 lines up with a 75 degree point, and 28 lines up with like 80 degrees. So you're setting it for 26 and 75. And there's been some argument that, well, that doesn't really comply with the code. But it actually does comply with the code. If you look at note B down at the bottom that I'm highlighting, devices with selectable set points will be within 2 degrees and 2 BTUs of the set point listed. So I can make this 26 to 30 BTUs, and I can make this 73 to 77 degrees if I need to be more adjustable to find a product that works. But essentially, I'm in that ballpark of 28 and 75. For you guys that love Psych Charts, which I'm sure everybody loves Psych Charts, and it wouldn't really be a PE meeting if we didn't have one. So you guys know temperatures along the bottom axis, absolute humidity is at the vertical axis, the relative humidity are the curved lines, 50%, 60, 70%, and so on. You guys know the drill. With the old economizer, historic set point of being 55 degree changeover point, that's that dotted black line. Now my new changeover point is basically 70 degrees, right over here on the yellow line. So if it's below 70 degrees, I am in a economizer mode. If it's above 70, I am in a compression mode where the red line is. All right. All right, so expanding on that, if I do the enthalpy version, then instead of that vertical line, I'm following these enthalpy lines. So these are my enthalpy lines over here on the Psych chart if you didn't know that. All right. If I find 28, it's right here. I draw my line down. Boom, I'm good there. But I don't really want a dry day where it's 100 degrees. That's not really going to work for me. So I have the 28 enthalpy number, and I have the 75 degree temperature cutoff number. So essentially my real line ends up looking like this, where my red dot is down that way and then down this way. So everything in this area over here is all becoming an economizer day, and everything over here or above here even is going to be a compression day. This is nice because when I was doing temperature only, this triangle always kind of worries me, right, where it's a 90% day, but it's only like 70 degrees out. I don't really want that day, right? So doing enthalpy eliminates this triangle where I have humid but mild days. All right, so I also have to do an economizer that's integrated. An integrated economizer is required by code. What an integrated economizer means is that my economizer damper has to work simultaneously and in conjunction with the compression when needed. It does require me to use the economizer first, so I cannot turn the compressor on until I've opened my economizer 100%. Then I can engage compression if needed. So if I'm trying to get down to 55 degree supply air and it's only 67 degrees outside, Obviously, the best I could possibly do would be 67 degrees supply air plus fan heat. So I'm not going to get there. So my damper is going to go wide open. I'm going to get 67 degree air, which is better than the 75 degree return air I would have gotten. But I'm going to have to turn my compressor on to take it the rest of the way. So an integrated economizer is required by code. No doubt about that. There are two other sections to this, number 2 and number 3 down here, that I don't personally feel have anything at all to do with an integrated economizer whatsoever. So we're going to talk about those a little bit later today because they really belong, mentally, they belong in another section of the discussion, not this section. So we'll come back to those two in a little bit. When I have the integrated economizer, my psych chart might look more like this, right? So essentially, if it's below 55 degrees, I should be able to get all the cooling done with the economizer. If it's above 75, I'm going to have to use compression, right? If it's between those two, I'll probably use some combination of those two things, right? So that's why I got this extra section on my chart over here now. You probably have seen stuff like that before. By the way, to do an integrated economizer, you have to have a 2-stage thermostat. The Y2 command off of the thermostat, the second stage command, is what actually energizes the compressor. If you have a 1-stage thermostat, irregardless of how awesome your rooftop or your economizer are, you're not going to get integrated economizer. The thermostat on the wall has to be a 2-stage stat, even on a 1-stage compression unit. So just keep that in mind as we go through. All right, if we're using our same little software tool over here, we got our entry-level unit in column 1, we got our code unit in column 2. Now column 3 is a code unit, plus I check the box saying that I have an economizer. Everything else is absolutely identical, right? So I'm saving 1% energy in Chicago from going from an entry-level unit to a code unit. I'm saving 7% if I go to a code unit with an economizer. So the economizer's got a pretty decent cost savings associated with it. Yeah, it's only $166, but this is only a 10-ton unit. Obviously, the bigger the unit gets, the more dollar savings I'm going to have. All right, a couple other notes on outside air economizers. If I'm going to suck more air into the building, I have to have a way for air to get out of the building. So I have to have a means for relieving the pressure. On small units, this may be a barometric exhaust, right? As pressure builds up in the space, a barometric damper on the return side of the system in the rooftop opens up and relieves that pressure. As systems get bigger, I probably want power exhaust fans to be doing this work for me. I also have to think about, well, both logic and the code. So a normal package rooftop, every rooftop unit you've specified, installed, or serviced in your whole entire life probably, except for DDC ones, but all the regular non-DDC units, whenever the fan turns on, the economizer automatically goes to minimum ventilation position. It doesn't matter if it's in the middle of the night. It doesn't matter why the fan turned on. As soon as the fan turns on, we open up the damper for ventilation. So that means unoccupied times in the middle of the night, we get a heating call so the building doesn't freeze or whatever. We start ventilating with outside air for a building that has no people. The ventilation codes do not require us to ventilate when no one's there. And the energy code actually tells us we're not supposed to do it, right? So the energy code says that whenever the building's unoccupied, I have to schedule the dampers to go fully closed, regardless of where my outside air dampers are. In this case, my economizer is my outside air damper, so my thermostat has to tell, or somebody has to tell my damper, go closed at night when no one's there, or go closed whenever no one's there. So one of the easiest ways to do that is to buy a thermostat that has an extra output on it for occupancy, because the thermostat is probably the only thing in the building that knows the occupancy schedule, assuming someone programmed it. So whenever the stat goes unoccupied, it sends a signal up to the damper for the damper to shut for ventilation reasons. The damper could still modulate open for free cooling economizer reasons, but it won't open for ventilation reasons. So you need to have that interlock for all outside air dampers, including economizers. Additionally, all outside air dampers need to be motorized, and they need to be rated as low leak dampers per AMCA 500D standard. There are exceptions where the damper does not have to be motorized, but we're not going to talk about those today because on a rooftop unit, as soon as I go to an economizer has a motor, so I'm automatically in the motorized area. So hence, all economizers in Illinois, irregardless of size, need to be low leak dampers. So if I put a 2-ton rooftop on a unit, I'm not required to have an economizer by code, but I am required to have an outside air shutoff damper, and if it's motorized, it's going to have to be this low leak scenario. So if you put a 2-ton rooftop unit on with an optional economizer not required by code, you still have to do what's on the screen here. So all economizers need to be low leak dampers. Basically, low leak, there's a couple major changes that happen there. One, is, we put the basic seals on the damper, the leading edges of the damper and on the sides, the blades. But the other major difference is that the gears, which historically have been inside the airflow path of the economizer, now have to move to the outside because the gears have to be able to move. Hence, if they can move, there's some ability for air to get through them. So having them on the inside airstream was not really helping us in terms of leakage. So now the gears have moved to the outside. Generally speaking, you can tell your rooftop supplier that you need a low leak economizer, and if you just say those keywords, low leak, they should know exactly what you're talking about, especially if they're in a state that follows the code. If they don't know what you're talking about, have them call me. So rooftop units historically have not been the most reliable, and there's multiple reasons for that, one of which is they don't get maintained like boilers and chillers do. They kind of get neglected, and they're on the roof, out in the elements, so lots of things could go wrong. But there have been numerous studies out there analyzing rooftops and what doesn't work on them. This is one study from like 10, 12 years ago now with 500 rooftops at 180 buildings. And we're going to focus on the economizer thing for now. But 64% of the economizers on those 500 rooftop units were not functioning correctly. They were either screwed shut, propped open, actuator fell off, actuator going the wrong direction, something like that, where basically they weren't opening and closing when they were supposed to do that. Interestingly, Honeywell did their own study, and Honeywell makes a lot of economizer controllers, and their number, 64%. Because of stuff like this, the code folks have started paying attention to the fact that we told you to put these economizers in, they're supposed to save all this energy, but if half of them aren't working correctly, what's the point, right? So now the code actually has a requirement where these things have to babysit themselves and track if there's a problem. So economizers, all economizers, need to have fault detection and diagnostics, FDD. That's been a universally adopted acronym, and as you know in our world, if there's an acronym, it's real. Title 24 in California uses the same acronym as the code here, and all the rooftop manufacturers know exactly what FDD means. And most of the thermostat manufacturers and economizer controller guys know what it is as well. So it applies to lots of types of systems, including packaged rooftop units. Here's all the requirements, which I won't read you in gory detail, but the economizer has to be able to detect certain problems if temperatures are out of whack, if the damper's not opening when it's supposed to, if it's not closing when it's supposed to, if it won't modulate it out, if you have too much outside air, if the sensors are messed up, whatever the case may be. There are multiple economizer controllers that can do that on the market, but you do need to ask for those things. If you just tell your supplier, give me an economizer, you'll get whatever they felt like giving you. Tell them I need a economizer with fault detection and diagnostics, or tell them you need a Honeywell Jade economizer or a Belimo Zip economizer or something like that by name, and then you're going to probably more likely to get what you want. So most of these things are built in. The economizer controller guys know how to do this. They have products that are quote-unquote stamped FDD. There's no rating system, but they're marketing in their literature as FDD, and it should be easy to find them. The one thing that makes it kind of interesting is item number 6. I'm going to read it to you, even though I'm not going to read code to you today for the most part. I'm going to read this line. The unit shall be capable of reporting faults to a fault management application, like a building automation system type thing, accessible by day-to-day operating or service personnel, right? So I can't have the screen on the economizer controller that's locked in the rooftop cabinet be my monitoring system. It cannot, because that is not accessible to day-to-day operating or service personnel. So it's got to be tied down to a building automation system, and then that BAS can pop up on my screen, or it can text message me, or something like that would be acceptable. But it cannot be the screen inside the unit itself. And if you go to the state website under interpretations, they will specifically tell you that. Or the last part of that is accessible to data personnel. Or if you don't want to do the BAS route, you want to have a regular simple system, you can enunciate the alarm locally on the zone thermostat. So if your thermostat can display the alarm message, then you can do it that way instead. These economizer controllers have an auxiliary output they can close when there's an alarm, and some of the thermostat manufacturers have an auxiliary input to receive that alarm. And those thermostats will be labeled on their product literature as FDD input or something like that. Or you can go to the state website. The state website actually has, I think I have it coming up in a few, but I think there's 3 manufacturers they've put on there. We'll talk about that, actually talk about that right now. Rooftop controls, this is what they look like for most rooftops. They're a little complex, but it's getting easier as time goes on. The controls for your rooftop unit, or any HVAC system for that matter, need to have certain things that they do. They got to be 7-day programmable, which you can easily get those thermostats. You got to prevent the heating and cooling set points from overlapping. There's got to be an override button, normal things. They got to have automatic start control. Manufacturers call this different stuff: intelligent recovery, smart recovery, adaptive recovery, optimal start, things like that, which basically means you tell the system you want to go occupied at 8 a.m. It calculates based on previous history and or weather data if it needs to start at 7:02 to get to set point at 8 o'clock, or if it needs to start at 7:30 or 6:51. So it starts each day at a different time to get you to set point exactly at the time you asked for. Your thermostat has to be able to do that for code. You got to shut the outside air damper like I mentioned. It doesn't say the stat has to do that, but something has to tell the economizer that it's unoccupied time and time to close its damper. I don't know what else that something would be. If it's not a BAS, because you don't have one, then it's going to have to be the thermostat because there's nobody else involved that has the schedule. I guess your lighting schedule panel might know the schedule of the building and it could tell you, but that would be weird. All right, so you got to have the damper shut off based on that. You got to find a thermostat that has that. And then you got to have a thermostat that has the ability to display these fault detection alarms as well. So when you do all these things simultaneously, I've found only 3 models of thermostats that can do that. Those 3 models are listed on the state website under the FAQ section on there. It's actually 2 manufacturers, 3 models. There could be other ones. Every once in a while somebody brings me one, but every time they show it to me, I find that they're missing one of these things. They might do the fault detection, but they don't have the ability to schedule the ventilation damper or vice versa. So be real careful about that. Demand control ventilation is sometimes required, sometimes not, just depends. If you don't know what demand control ventilation is, this is going to be the 60-second discussion on what is normally a 60-minute discussion. So this graph here is from a building, actually it's a building in Florida from years ago. I just keep using it over and over because I'm too lazy to make a new graph. But this is time of day from midnight to midnight down the bottom, and then this is percent of damper open with the very top at 100 being 100% of the ventilation air. Not 100% of the economizer damper opening, 100% of the code required ventilation air, which may only be 20 or 30% of the total CFM of the system. Right, but normal building goes occupied at 7 a.m. The damper goes wide open. It stays open all day long because nobody's ever interlocked it to a schedule, right? And then it shuts off at, what is this, 7 p.m. in this example, right? Boom. What demand control ventilation does is it uses CO2 sensors to detect the amount of people that are breathing in the space. The more people that are in the space, the more CO2 that's produced, and the more people in the space, the more ventilation air is required by code. Or you can think of it as the less people in the space, the less ventilation air is required by code. So if I have to have this code required amount of air by my red little arrow up here, and if less people show up, I can throttle it back. So that green hashed area is the normal code required air. Purple is what would happen if I was tracking the amount of people that actually showed up, right? Some people come into work late. Some people check out and go to lunch early. Some people, stay at office at lunch. Some leave. Some never come back from lunch at all because they don't feel like it. And then some of them cut out early and go golfing, right? It's like typical office building, just 2-hump type scenario. Everything between purple and green is energy savings because I'm not 100% occupied. I should be able to save energy there, right? And there's lots of scenarios like that. That's not just an office building thing. Pretty much every building has a profile like that. For offices, we call it the 2-hump profile. Restaurants have 3 humps, breakfast, lunch, and dinner. Schools have various profiles. Movie theaters, everybody's got a profile like this. And there's plenty of times that the building is not at design occupancy. And when it's not, we can cut the ventilation air back. Sometimes this is required by code. So when specifically is DCV required by code? First thing is to pay attention to is the density of my occupants more than 25 people per 1,000 square feet. The old code was 40 people per 1,000 square feet, right? So now we're at 25 people. For 2012 and 2015, it's 25 people per 1,000 square foot. So that's going to be like movie theaters, conference rooms, auditoriums, stuff like that. Maybe an office with lots of cubicles that are relatively small, those sorts of things. So pay attention to those, and you might have to put demand control ventilation in. There are some exceptions if you look down there for systems that are fairly small or systems that already have ERVs anyway. But for most of your, movie theater, auditorium, conference room type stuff, training room, classroom, you're probably going to have to do a CO2 sensor on your rooftop unit. So pay attention to that. So we'll add one more column on there. So entry-level unit, code unit with economizer, code unit with economizer, and DCV. One more checkbox, right? So that bumps us up to 13% savings. So just adding that CO2 sensor on top of the code compliant unit with Economizer was another 6% on top of the original 7% we were saving. And CO2 sensors are not that expensive, so there can be some significant energy savings there. Now, this is just for a particular example. Some examples will save more than others, and it depends on how many people you have and how many of them are leaving and coming and going kind of thing, right? But this is just an average office building type scenario for my example up here. All right, so the next thing we want to talk about is modes, right? So my rooftop unit has several different scenarios that it could be in at any given time, and this is off of a 2013 Pacific Northwest National Labs study for rooftop units specifically. They modeled, I don't even know how many scenarios they modeled, and then they went out and tested like 60 buildings that fit their model to make sure their model lined up with what they thought and all kinds of geographies and stuff like that. This is just a sample out of that 200-page report. The little red bars down at the bottom, that's how many hours that they ran heating in those particular units. The blue bars at the top are how many hours they ran cooling. Green was the economizer hours. Purple was integrated economizer, so both compression and economizer. Then baby blue was when they were doing neither heating nor cooling and they were just doing ventilation air. So the damper was at ventilation position and the fan was running. That is a lot of hours at just ventilation. So we can somehow magically make your rooftop unit go from 80 to 83% thermal efficiency on the heat side. Whoopee, right? We can make you do 14 IER someday on the cooling. Whoopee, right? The fan is what's using all the energy. The fan is the dominant operating source here. So as you probably noticed in other aspects of the code, the fans have been getting picked on. By picked on, I mean they've been requiring more efficiency in terms of different ways to do that. So here's one of those ways that comes up. This section of the code is really, really, really weird. All right, so this was not the way that this was intended to be. I've talked to people that are involved at IECC and ASHRAE 90.1, and this was not the intention, but this is the way it ended up. The intention was to make all systems have two-stage fans or more than two stages. However, when they wrote that language, they put it in section 403.4. And 403.4 in its entirety only applies to hydronic systems, which a normal rooftop would not be, or it applies to multiple zone systems, which a rooftop would only be if I put VAV dampers or VVT dampers or something like that on there. So essentially, you don't have to do the multi-speed fan unless you have zone dampers. If you have zone dampers, then you're going to have to put in a two-speed fan. Now, with that being said, if you put a two-speed fan on the rooftop unit at the manufacturing level, and the manufacturer does an AHRI test with the fan with the two speeds, you actually will result in a higher IER published number. So sometimes you may choose to do a variable speed or a multi-stage fan like this on an entry-level rooftop in order to get the rooftop to be code compliant. Instead of improving the refrigeration side and going with a higher refrigerant efficiency model number, right, I'm going to go with by putting this fan on. But if I have a zoning system, I'm going to have to put the multiple speed fan on, assuming it's more than 65,000 BTUs, which is essentially a 6-ton rooftop and up, 5.5 tons and up. So 6-ton rooftop and up. So keep that in mind on there. The way that essentially works, the multi-stage fan, you get two speeds of fan. There is one speed that is utilized for first stage of cooling and the ventilation only mode, right, which is a lot of the run hours, as you know. And there's a higher speed of fan that is used for second stage of cooling, any stage of heat, right? Those are the two airflow set points. So essentially, if I'm in only one stage of cooling or if I'm in vent mode, we cut back from 100% of the design airflow down to essentially 2/3 of the airflow. Some folks ask why we don't do multiple stages on the heat. There's numerous reasons for that, but the main reason is the Economizer controller has to have the ability to have dual minimum airflow set points. Because if I slow your fan down and I don't change your Economizer minimum position, you're going to get less code required ventilation air. So I have to have an Economizer controller that can intercept these signals from the thermostat and be smart enough to say, oh, you want one stage or two stages of cooling? Oh, I go to a different minimum position for those two scenarios. And right now, the only Economizer controllers like that do 2 minimums at most. No one does a 3 minimum scenario yet for Economizer control. So let's see how much energy that saves. If I take my code compliant unit, which is an IEC 2015 IER type unit, plus the Economizer that's usually required, I take that exact same unit, same model, same everything, and all I change is by putting a 2-speed fan on it instead of a 1-speed fan. I'm going to save about 30% energy. So that's a pretty hefty chunk of energy savings from going from a 1-speed fan to a 2-speed fan. Now, just so you guys are aware, we typically don't make 2-speed motors anymore because that's fairly costly to have double windings. So pretty much you're going to get a VFD that's programmed to only run at 2 speeds, right? That's how we're doing the 2-speed control. But if you remember, going from an entry-level unit to a code-compliant unit only saved me 1% energy. So instead of doing that, if I make my entry-level unit code-compliant by putting a staged air fan on like this, I'm going to get a lot of real savings to go along with my code compliancy. All right, last one, and we'll get another couple questions in here. I said I would come back to the integrated economizer discussion, right? And we talked about integrated economizer being required. We talked about number 1 here. You got to open up the damper fully before you start using compression. That all makes sense. But number 2 and number 3, in my mind, never really fit in this section. And anyone I talk to doesn't think so either. So the first one is DX units that have integrated economizers that are above 75,000 BTUs have to have no less than 2 stages of capacity. Well, anything above 54,000 has to have an integrated economizer. So essentially what this is saying, if you're above 75,000 BTUs, you have to have 2 stages. You cannot put in a 1-stage 10-ton unit anymore. I know people do this. It was always stupid before. It's still stupid now, but the code doesn't allow you to do it. So 75,000 BTUs is essentially anything more than 6 tons is going to have 2 stages of cooling minimum. And everyone reads that, interprets it the same way, and everyone's pretty logical on that. There's been no debates or arguments at the state level. The one that gets debated is number 3. Other DX units, including those that control space temperature by modulating the airflow to the space, shall be in accordance with the below table, which basically says I need 3 or 4 stages of cooling for some of these systems. When I read those that control space temperature by modulating airflow to the space, I'm thinking zone damper system. If I have a VVT or a VAV zone damper system, the thermostat tells the damper to open more or open less depending on how much cooling it wants, right? So to me, that's controlling space temperature by modulating airflow to the space. So to me, as soon as I hear there's a zone damper system, I'm going to go to 3 stages or possibly 4 stages if it's a big unit. And that's a good idea anyway, because the more stages of cooling, the more dampers I have on the system, the more stages I'd like to have to be able to throttle back to. So it makes sense from a logical standpoint, but it's very well code compliant here. Now, with that being said, other people have interpreted number 3 differently, and they say other DX units that modulate space. So not that the DX unit that is being modulated by, not that the dampers are being the ones modulating the airflow, but that the DX unit itself actually modulates the airflow. So in other words, they're taking a very literal interpretation and saying, oh, yeah, if the unit modulates airflow, then you have to do it. Which then would mean anybody that had to do the 2-speed fan, go back a little bit here, anybody that was doing this 2-speed fan would hence also have to do the 3 or 4 stages of compression. So I don't think you want to interpret it that way, but either way, if you did, it's still going to be linked back to having a zoning system or a hydronic coil. So it ends up being the same discussion no matter which way you want to literally interpret that language. As soon as you put zone dampers on, plan on having 3 or more stages of cooling compression. I got a feeling that this one is also one that'll start evolving into more and more units, not just zoned units. But right now, it's just zoning only. All right, number 3, and then I'm going to answer some of your guys' questions I saw you typing in here. Which of the following are required on a typical 10-ton DX RTU installation? When I say typical, I'm talking about a DX unit with gas heat, that kind of stuff. It's not some kind of weird custom unit with hydronic coils or anything like that. It's a typical 10-ton off-the-shelf DX unit. Which of these things do you have to do, right? So my choices are 12.6 IER, integrated economizer, fault detection and diagnostics on the economizer, 2 stages of cooling. So I'll give you guys a chance to answer that while I go read a couple of your questions. All right, so Mark asks, does a carrier RTU furnished with a programmable stat be a 2-stage cooling and closed-away damper during unoccupied periods? So I don't know, I'm going to say carrier RTU. The carrier RTU is independent of the thermostat, but if you are local in the Chicagoland area, meaning you're a customer of Temperature Equipment Corporation, when we bid you a code-compliant rooftop unit, we do all these things. We make sure it meets the efficiency, make sure you have the economizer, and we give you a thermostat that does the intelligent recovery. We give you a thermostat that does the 2-stage capacity for integrated economizer. We give you a thermostat that will have an extra terminal on it to close the outsider damper during unoccupied periods, and it has a input on it for the fault detection and diagnostics. So we normally bid that with a Venstar T4900 thermostat, which does all of those things and meets the code, and it's the most cost effective. There are 2 other ones from Honeywell that we bid sometimes. Those ones cost a little more money, but they require less wires. So there's kind of a trade-off there on the installation labor versus the product cost. So we bid it both ways depending on what someone may have told us about this. All right, let's close our poll question in 5, 4, 3, 2, 1. And you guys did great on that one. 95% of you said it was E, all of the above, right? I know you probably didn't have 12.6 memorized, but if you knew it was B, C, and D, which you should have known that from listening, you probably would have got it right, right? All right, so that moves us to question number 4. So question number 4, if a zone system is applied to that same previous 10-ton rooftop example, which of the following is also required as a minimum? Not every job, but a minimum. Excuse me, every job. Sorry. If a zoning system is applied to the same 10-ton rooftop example, which of the following is required as a minimum? Right, so every one of those has to do it, kind of thing. So your choices are A, 3 stages of cooling, B, staged air volume or variable air volume, C, demand control ventilation, or A and B, or A and C. It's a little trickier than the last one, but hopefully everybody can get it. And while you're doing that, I'm going to read another question. So Greg says, doesn't fault detection diagnostics capable mean just that? If the RTU has FDD that don't communicate status to any BAS, still seems to meet code based on how the code is written, the unit is still capable of performing. Okay, I got your question. All right, so let's go back to that. Oh, I can't go back to what you guys are on this screen. As soon as this screen's done, I'll go back to that and I'll explain what Greg is asking, because that's a very common question. I know exactly what you're talking about, Greg. Only 46% of you voted, so I'll still give another second here. Okay, if you have not voted, please do so. I will close it in 5, 4, 3, 2, and 1. So actually only 58% of the people got it correct, which was A and B, 3 stages of cooling and staged air volume or VAV air volume. So you have to have multiple stages of cooling with a zoning system, and you have to have multiple speeds of fan. All right, so let's answer Greg's question, and then we'll finish our last few slides here. So Greg's going back to FDD real quick because it's a very common question, so I want to go back to it. He's saying here the unit shall be capable of reporting faults. So he's saying capable, but I don't actually have to do it in real life. And I understand that, and I understand the linguistics of it. The way the state has interpreted it is thou shalt do it. You have to do it. If you go to the state website that I gave you earlier and go to the FAQ section, they're going to tell you that you have to do it. The intent of this is to make you do it. The rooftop unit has to be capable of doing it, and someone has to actually make it do it. But I understand what you're saying. As someone who used to bid, plan, and spec jobs for control systems in the 1990s, I know exactly the difference between thou shalt do it and thou shalt be capable of doing it. The state has interpreted those to be the same thing. Thou shalt actually do it. But I understand your point, Greg, and it has been a point of confusion for some folks. But you better have a thermostat that does it. If your local inspector is getting good at policing the code, the state's telling them to police it that way. All right, last few concepts here. All right, ERVs, we don't have time to talk about that either because ERVs are a whole other hour in and of themselves, but ERVs save energy by saving energy from my exhaust air stream and transferring it to my ventilation air stream. So obviously the more ventilation air or the more exhaust air that I have, the more energy savings potential there will be. If you don't have any ventilation air, you don't have any exhaust air, this doesn't do anything. There are times that this is code required. This language has not changed since the previous version. The tables have changed, but this language hasn't changed. The first thing to point out is that the ERV must be 50% enthalpy recovery, right? So if you have a sensible only wheel or sensible only plate, That means you're going to get a certain percentage on the sensible side and you're going to get 0 on the latent. So when it comes out to averaging out for the total enthalpy, you're not going to be able to comply. You cannot put in sensible only wheels or plates. You have to do enthalpy wheels or enthalpy plates in order to do this and accomplish it. So if you're putting an ERV in for code compliance, make sure it does enthalpy. There are some exceptions to this and when you might not have to do it, right? And I'll leave that for another discussion because those have not changed since last code cycle. What did change is the tables. So we're climate zone 5A, and it used to be for us on the previous version of the code, we only had the 30% and larger tables. So if I had a 5500 CFM supply fan with 30% outside air, I would have had to do an ERV. If I had less than 30% outside air, there was no requirements at all. Now I have a column for 20% and a column for 10% outside air, although granted it does apply to fairly large fan systems. So those two columns are new for 10 and 20%. The other thing that's new is the entire table on the bottom. They added a whole new table on here, and if you look at that, all sizes for climate zone 5A, doesn't matter how big my rooftop is, if I'm bringing in more than 10% outside air, I'm required to have an ERV if my system operates more than 8,000 hours per year, right? So there's like 8,760 hours in the year. So essentially, if I have a 24/7 occupancy project, I'm going to need to put an ERV on there unless one of those prior pages of exceptions applied to me. Take my code example, rooftop unit, everything's identical on there. The only thing I changed is I added an ERV. And this was the potential savings for that example, 7%. Now, the ERV savings varies widely. This was 7% on this quote-unquote typical 10-ton office building we were looking at. But my savings is dramatically different for places that have lots of people, right? So like an auditorium or something like that. So we use charts like this all the time, and we also do calculations for very specific systems. But usually the cutoff is if I get more than 1,500 CFM of outside air, the payback column starts looking really attractive for ERVs on rooftops. And this particular chart in its entirety was developed with rooftop examples. So smaller CFM outdoor units, not so great. When I get to the larger CFM, 1,500 and up, the paybacks all tend to be under 2 years, right? They get really attractive really fast. But we'll save that for another discussion. So if we look at all the stuff we talked about today and put it all out there together, right, I can't say all the things I saved and add them up and say, oh, you're going to save 105% of your energy. That wouldn't make sense because some of these things overlap with each other. So this tool is kind of nice and I can compare multiple things. So in this case, I took a typical 15-year-old unit that is about ready to die, R22, 15 years old, standard efficiency, nothing sexy, right? No economizer, whatever it was. And now I'm going to take that off the unit, put a code unit on, or a code unit with economizer DCV, economizer DCV staged air volume, economizer DCV staged air volume ERV, or all of that stuff on the highest efficiency model number that I can find, plus multiple stages of compression, like fully loaded, Cadillac, deck it out kind of thing. All right. So here's my energy savings for all those particular scenarios. Right. So just going from the existing unit to the code unit, 15-year-old unit to code unit is going to save me 25%, $800 in this example for Chicago. And the economizer, 932, right? With the DCV, a little bit more. With the DCV and stage air volume, that's the biggest jump from 33 to 53% right there. That's the biggest jump of adding things on. Adding the ERV on. Now, the ERV is not giving me a lot of payback because a lot of these things overlap with it, right? Especially the CO2 sensor. And then fully loaded, Cadillac, every single option I could possibly find, 62% energy savings, $2,000 savings compared to the entry-level unit, all right? So that's just, it gives you an example. And then obviously next week we're going to use the software. If you're interested in using the software, it's available for free. I can help you get the software. And then next Monday we have a webinar on how to use this software. So let's wrap it up with the last thing being the ductwork, because someone did ask about that and it does tie in. Now ductwork is not specifically a rooftop thing either, but obviously all rooftop units have ductwork, so this kind of applies. We got to go through it fast because we only have like 2 minutes left on the clock here. But systems are very leaky. Ductwork is very, very leaky. My house was leaky before I sealed it. Every commercial building I've been to has leaky ductwork. When we tested, it's leaky. When we sealed, it's leaky. Just know that it's pretty bad, and all these slides reference back to various tools to help you illustrate how leaky ductwork is. It is a major, major problem, right? If you guys are specifying systems and you specify the typical duct leakage class of 200, I'm not going to go through the math right now because of time, but that's about 3,000 CFM leakage on a 10,000 CFM system. If your leakage class in your specs is 200, you're basically saying I am okay with 30% of my outside air leaking. Generally, we suggest you target a class of 4, or class A system, which would mean in an example of 10,000 CFM, only 62 CFM would be allowed to leak. That would be pretty significant over the typical 30%. On average, 10 to 20% of the air that goes through your supply fan never, ever, ever, ever reaches the occupied space, right? 30% of it's leaking, but some of that leakage makes its way to the ceiling cavity into your space. The rest of it makes its way out the sidewalls or out the roof line or somewhere else, right? So it's a pretty big problem, and it's pretty easy to solve. The code does require duct sealing and duct insulation. So first off, your supply and return ducts and plenums need to be insulated to R6 when they're in unconditioned spaces. And then if they're in outdoors for our climate zone, they got to be R12. That's a pretty big increase. So if you have ductwork that's running outside, example, a rooftop unit with side discharge, horizontal discharge into the side of a building, that's going to have R12 insulation. So plan that ductwork being much larger because the insulation is probably going to be on the inside. All ductwork has to be sealed. Ducts, air handlers, filters, everything have to be sealed, right? For low and medium pressure systems, you have to seal them, but you don't have to test them. If you go to a high pressure system, which means 3 inches and over, you got to seal them and test them. That's probably not a rooftop anymore. So for rooftops, you got to seal the ductwork and insulate the ductwork, but you don't have to test the leakage. Bigger systems, you would have to do that. All right, last slide, and then we'll have our last question, and then we'll be wrapped up here. The additional efficiency package, probably the biggest source of confusion on all the questions I get, and I probably get, I don't even know, 5-7 energy code questions a day. There used to be 3 parts to this. Now we're up to 6 different options. Every project you do will say in the code, you got to also comply with section C406. And when you come over here and read it, it tells you that you have to do one of these 6 things, not all of them, just one of them, and you pick whichever one you want. It used to be make your system more efficient for HVAC, or make it better for lighting, or do the renewable energy, right? Now they've added some enhanced lighting controls, dedicated outside air system, or service water improvements, right? So you can pick any one of these. Most of the time, option number 2 seems to be the one that the architect or the building designer chooses. The lighting power density, it's the easiest one for them to hit in most applications. But sometimes they go the HVAC route, and they tell you that you have to do 406, or they tell you have to do 10% better, or they just give you some chart of things you have to do, right? I pointed out in the rooftop example because to get 10% better on the cooling and heating, that means my 80% efficient heat exchanger on my rooftop is now going to have to be 88% efficient. Well, guess what? Nobody makes that, or hardly anybody makes that. I think somebody makes like a little niche 5-ton unit or something, and somebody makes like a super custom air handler rooftop unit that will do it. But all your normal rooftops, all your normal Carrier, Train, Lennox type stuff, they don't have anything like that. That is that high efficient on the heating side. So as soon as your architect tells you that we're going to go number 1 on this chart, and it's going to come from the HVAC side, you need to be prepared to say, okay, that's fine, but now the rooftop design's off the table, we're going with chillers and boilers. That's what you're going to probably have to do, or something even more extreme like geothermal or something like that. So if they want it to be a rooftop job, they got to not go number 1 on here and go to one of the lighting routes or one of the other things. All right, our final question. Question number 5. True or false? All rooftop supply and ductwork must be sealed. Let me see if there's any more questions. No pending questions. Looks like most of you guys are getting the poll question answer correct, so that's good news. Looks like most of you have actually answered already, so that's good news. So we'll close it in 5, 4, 3, 2, 1. And 87% of you said that is true, which is correct. All ductwork on rooftops or any other ductwork must be sealed. All of it has to be sealed. You only have to test the leakage if you get above 3 inches, but all ductwork sizes need to be sealed. All right. So that is going to wrap us up unless you have further questions. Here's some of the normal type of resources that we use today. If you didn't write them down previously on different slides. And then I'd like to thank everybody who allowed me to essentially borrow their graphics so I don't have to create my own from scratch because I'm not a very good graphic artist. If anybody has any other questions, they can type them in right now and I'll try to answer them. Or if you're not going to type them in now, you can contact me later, and I will try to respond to you then. For those of you guys that needed PDHs, professional development hours for professional engineers, tomorrow these quizzes, the poll questions will get graded, and then they'll start typing up the certificates. There are hundreds of you on this webinar, so it will take a little bit of time, but as always, we'll try to get them out to you in about a week, and they'll come to you via email if you passed. If you didn't pass, you probably already are aware of that. You would need to answer 3 of the 5 questions correctly to pass, which is 60%. One of the questions was a little tricky, but the other 4 were very straightforward. So everybody should hopefully been able to get 60% passing rate. If not, I apologize. We do have one more question before I was about to log off. Tom asks, do we need to insulate ducts in the plenum return ceilings? That's a great question, Tom, and that depends on whether your plenum return ceiling is considered unconditioned or not, and that's always been a debatable discussion. So, if you come up here, return duct plenums shall be insulated with a minimum of R6 where located in unconditioned spaces, right? So unconditioned spaces, most of the time your return plenum, if it's a return plenum, it is not unconditioned because the return ductwork is the ductwork. The ceiling plenum is the return ductwork. So that is conditioned by definition. So you would not need to insulate that for energy code purposes. However, as you're probably aware, the supply duct, if I run it to the return plenum, I don't insulate it, it very well could sweat. So I'm probably going to want to insulate it for other reasons other than energy code. So the energy code, the answer is no, Tom, but from a good application standpoint, yeah, I would insulate my supply duct when it's inside my return plenum, because you could have some condensation issues when you run 55-degree air through a relatively humid space, and plus you also lose some of your BTU capacity that leaves the ductwork and goes back immediately into the return side instead of going into the space. So I would insulate it even though the code doesn't currently require you to do that in your scenario. All right, I think that's all the questions. So I thank you guys for your time. And if you have any further questions, you can send them to me later. Thank you very much.